Hello, and welcome to another video session. Today we're going to be talking about, or this video is going to be talking about anaerobic digestion, part 2 of 2. So many people talk about the exams for the wastewater exam levels, class A and B and C here in the state of Florida. We talk about the amount of anaerobic digester questions on the test. And when you get into the B level and into the A level, the exams get a little bit more comprehensive and conceptual, and you have to start applying some of your knowledge rather than just, memorizing certain things about digesters. Now you have to do a little thinking about troubleshooting and looking at some data and things like that. So as you get into the B and the A level, the exam questions on digesters obviously get a little bit more tricky, a little bit more tough. There's no trick questions, but they're just tricky because they make you think. When you get to the A level exams have more process control on the exam than the B level does. So there's not so much just questions about digesters like troubleshooting, but we get into more process control. So that's what this video is about. We're going to talk about anaerobic digestion process control. So several things that you're going to need to know about. We can watch in the other video. Part 1 talks a little bit about the layout of the digesters. It talks about the covers, the tilting of the covers, struvite, all that fun stuff. This one's going to be kind of going into how do we run the digester, and what do we monitor and use for troubleshooting. So I'm going to kind of go ahead and get into this. Let me do something here and move my little panel out of the way here. And we're going to pull up the presentation. And I'll move this out of the way. And let's go to slideshow. And off we go to the races. All right, digestion part 2. Process control. Dun, dun, dun. So we got our copyright statement, as always, in our videos for the University of Florida TRIO Center and Center for Training, Research, and Education for Environmental Occupations. And my contact information is shown here. And you can always look us up on Facebook and LinkedIn. And please visit our website at uftrio.org. And if you have any questions or comments, my contact information is here, and it's also at the end of the video. The references that I used to put this presentation together come from our training manuals that are approved for the state exam. Now, the California State University Operation of Wastewater Treatment Plants, Volume 1, Volume 2, and the Advanced Treatment is included in there, but it's mostly Volume 2 that has this material in it. So that's the big one that if you wanted to look this stuff up, you can find most of it right there. So we talked in the first video about anaerobic digestion, and we said that anaerobic digesters generally have 2 separate tanks. We have one that's usually known as a primary. I'm just going to label this one primary anaerobic digester, and then we have a secondary. And that's going to be important for us in this discussion because all the activity is occurring in the primary digester. When we pump sludge into the digester, the raw sludge in, these digesters are usually really well mixed. So we're going to make sure that the sludge is mixed and the temperature is constant and all that. We're going to be actively digesting or breaking down the volatile organic material in here, otherwise known as volatile solids. And we're going to produce volatile acids, and we're going to produce methane. And then we're going to pump some sludge over into the secondary and let it, kind of settle out and all that. So we got 2 tanks set up, but the secondary digester will become important for us here in just a little bit. You'll see a little bit more why we want to have some good sludge in that tank. So remember, it's a 2-step process: acid formation, methane formation, mostly inside the primary digester. The digester layout is normally like this. I kind of showed you already in the one picture. And we've got our little layout here. And this is again, showing you the raw sludge feed coming in. This raw sludge, remember, can be primary clarifier sludge. I'm going to write up here, primary clarifier. Remember, a primary clarifier makes a really thick, viscous sludge. So that could be primary clarifier or secondary waste activated sludge flowing into the digester. So it's usually thickened, some kind of gravity thickener or some kind of thickening device to get the sludge thick, so we're not putting so much water in the digester. So the first tank is the primary that receives the raw sludge feed, and then we transfer over to the secondary. So again, that was kind of covered in part 1, so you can go back and review that if that's still kind of foggy. So what's happening inside the well-mixed primary digester? So this is kind of showing you a little bit of the layout of how the bacteria are doing, let's say, over a period of time. So the sludge is fed into the digester. That's the organic matter that you see here. And we have bacteria living in the tank that also live in a symbiotic relationship with the methane formers. But we generally have acid forming bacteria that are ready to go and hungry to break down this organic material under anaerobic conditions. So they're considered facultative anaerobes, and some of them are strict anaerobes. So they're operating without oxygen, without nitrate, nitrite. There may be some CO2 present, remember, or even sulfate, making some hydrogen sulfide gases along with this. But the main thing is that these bacteria are attacking the carbon coming into the digester. We call that first stage stabilization. And these bacteria produce organic acids. Sometimes we call these volatile acids or volatile organic acids. So volatile acids, I'm going to write it up here, volatile acids are being produced. We abbreviate that VA, okay? VA for organic acid, volatile acid formation. Think about what I have here in front of me here is this little bottle of white distilled vinegar. So this is considered acetic acid, or a weak form of acetic acid, but vinegar. And it's similar to some of these volatile acids that are being formed in the digester. There's acetic acid and propionic acid and valeric acid and butyric acid all being formed, but those are volatile acids. The volatile acids then are the food source for the methane forming bacteria. So the methane formers will use the organic acids as a carbon source, and they will produce for us two separate things, or in this case, we're just only going to worry about two separate things. I mean, obviously there's more things happening biologically here, but we're going to just focus really for this video on what's being produced here. We have CH4, which is methane, and CO2, which is carbon dioxide. So in the biogas is roughly about 70% CH4. And we said in our previous video that it's roughly 30% CO2. Now, these numbers can vary, obviously, but that's kind of a general rule of thumb. So the biogas is methane and carbon dioxide. And remember, it also has some trace gases like sulfide and other things. And these bacteria also produce some alkalinity. So that's really important, because alkalinity that's produced by the methane formers is a buffer against the volatile acids that are coming in. So these bacteria kind of make an alkalinity that buffers or neutralizes some of the acid. Now, the methane formers are the sensitive organisms, a little bit more sensitive than the acid forming bacteria. So we're going to be trying to pay attention to the health of those methane formers. And we can kind of gauge the health of the methane formers by this ratio of gas. So we said this was biogas right here. And if the biogas is this ratio or close to it, we know that the methane formers are doing their job and they're probably healthy. But if the biogas starts to be less methane and more carbon dioxide, then we think, or we would know that something is not right. So, but that's a good indicator of what's going on inside the digester. That's why we monitor those gases. the alkalinity is formed by the methane formers that helps buffer this volatile acid. So what I'm going to talk to you today about is a ratio of volatile acid to alkalinity. And we're going to use those numbers from our laboratory results to gauge what's going on in the tank or in the primary digester. So a proper operating range or proper amount of volatile acid to alkalinity would look something like this. We'd have 0.1 parts or milligrams per liter, or however you want to word this. We're just going to say milligrams per liter for this example. 0.1 milligrams per liter for every 1.0, one whole part of alkalinity as milligrams per liter. So 0.1 to 1 is the numbers we're looking for. So it's a very small amount of acid for every one whole part of alkalinity. So think about if you had, 10 boxes of this Arm & Hammer baking soda. This is alkalinity in the form of sodium bicarbonate in this baking soda box. So this is alkalinity, and you had 10 boxes of this for every one bottle of acetic acid. So 10 of these to one of these would be the ratio. Or let's just say if you have one box of this alkalinity, then we'd only want 1/10 of this acid to make that ratio. So it's quite a difference. A lot more alkalinity is needed to maintain the health of the digester. So again, this is the process control test that we use to run this facility. Now remember that volatile acids tend to consume alkalinity or take up alkalinity. And also, if the alkalinity is not present, then the pH could actually start to fall. But if everything's working right, even though acids are forming, the alkalinity buffers it, and we generally don't see a pH problem in the digester. If you actually use pH as your only process control tool, and the pH is, if you notice the pH is falling or decreasing and it's not in the proper range, let's say you measure your pH and it's 5.5 in your digester, well, you've already consumed all your alkalinity. Your digester is already sour by that point. That's why pH is not a recommended tool to only monitor for the digesters. It's better to do this as your process control. So volatile acid alkalinity ratio is the key to the digester operation. So when the volatile acid alkalinity ratio gets out of balance, the digester is said to be upset or sour. There's another word for it. I'm not sure the history of the word, where it came from in this particular case, but in some cases, operators have called digesters that are sour, we call them stuck. Maybe they're stuck in the acid formation and they never made it to the methane formation. Maybe it got stuck in between the two ranges. I'm not sure if that's the history of it, but it makes sense to me. So the volatile acids, or known as VA, remember we said this is VA for volatile acid, they're considered short chain organic acids. Like I said earlier, acetic acid is vinegar, propionic acid, butyric acid. These are all formed by acid forming bacteria. They're saprophytic types of organisms that grow anaerobically and don't require an oxygen source, but they will still be able to thrive. So alkalinity is abbreviated like this. Alkalinity sometimes is just abbreviated ALK. It is actually produced by the methane formers. This can be supplemented chemically by using lime, sodium bicarbonate, which is what I had here in the box of baking soda. We have sodium carbonate, which is essentially soda ash. I'm going to write that on here, soda ash. And ammonium hydroxide can be used. We can also find, in some cases, magnesium hydroxide is used. And I'm going to write that up here, magnesium hydroxide. is sometimes used. So there's other chemicals that can be used. Lime is essentially calcium oxide, and it's wetted to form calcium hydroxide. So you can use different forms, but alkalinity is generally produced by the methane formers. So here's our number again. We're going to repeat it for a reason because it's super important for you. So you see it written in writing here. So 0.1 to 1 is considered a good balance. If you had, let's say we had 100 milligrams of alkalinity available, let's just say this, alkalinity was 100 milligrams. Well, what is 1/10 of 100? So 1/10 of 100 is 10, right? So 10 milligrams. And just another example, if we had 100 milligrams of alkalinity, we would want no more than 10 milligrams of acid. If you came out of the laboratory and you said we had 10 milligrams of acid, I would say, great, I hope we have at least 100 milligrams of alkalinity. So you can kind of see, you can word this a couple of different ways, and that's what you need to recognize for the state exam. They do word these things different ways. You got to be familiar with this terminology. For every 1 pound of food that's fed to the digester, in this example shown above, there should be about 10 pounds of alkalinity available. So kind of showing you this, for every 1 pound of food you send up there, you should have about 10 pounds of alkalinity, which would be the 0.1 to 1. So the alkalinity numbers generally should range between 2,500 to 5,000 milligrams per liter. That's generally what the bicarbonate alkalinity is, the range of most of these digesters when they're operating optimally. So to maintain the proper volatile acid alkalinity ratio, what would the range of the volatile acid be? So remember, we want 1/10 of the acid against one part of alkalinity. So 1/10 of 2,500, 1/10 of 2,500 is 250, essentially just dropping one of the zeros off in a way. And then 1/10 of 5,000 would be 500 milligrams per liter. So the range of the volatile acid would be that. So 250 to 500 milligrams per liter. So there's our answer on the bottom of the screen. All right. So the range changes, the ratio changes when we don't pay attention to how we're feeding the digester. And if we leave the raw sludge pump running too long, or we have too much sludge in the primary clarifier, and we're trying to get that sludge out of the primary clarifier, maybe because of odor complaints or whatever coming from the primary clarifiers, sometimes we tend to pump too much sludge too rapidly into the anaerobic digesters. So it causes the ratio to get a little bit out of balance. So a 0.3 to 1 is where we're starting to get more volatile acid for every 1 part of alkalinity. So we need to pay attention to this, but we don't panic. We don't panic at this point because it's not an upset condition yet. What we want to do is keep it mixed, make sure that the mixer is running, make sure the temperature stays constant, and I would say decrease or stop the sludge feed, and don't take any sludge out of the digester as far as transferring over to the secondary digester. Just leave it kind of rest, just like when you don't feel good and you want to take a day off and just kind of just lay in bed and get over the flu or a cold or whatever. Think about it like this and say, well, it wants to just rest. Don't try to keep feeding it, and it will recover because the bacteria, the methane formers, will produce they will consume the volatile acids and they will produce alkalinity. So this number will come back on its own once the methane formers can kind of keep up with the acid that's being formed. So they'll recover and they'll produce some alkalinity. So let it rest, let it recover on its own. I know how I feel when I'm not feeling too good, how I act when I'm not feeling too good. I just want to be left alone. Just leave me alone. I'm not going to eat much. I'm just going to rest. All right. What happens if we don't pay attention to this and we keep feeding the digester? Well, if you get to 0.5 to 1, let's say a half of the volatile acid into 1 whole part of alkalinity, now we're in trouble because we're getting so much acid now that we're going to start to have some problems. Just for instance, if you said to me that you had 2,500 milligrams of alkalinity present, And then you came back from the lab and said, but half of that is acid. Well, half of 2,500 is, I believe, 1,250. So this would be 1,250 volatile acid, and that's a lot of acid for that amount of alkalinity. So got to really pay attention to these digesters. Now we're getting into trouble when we have numbers like this. The biogas mixture may now be looking more like 65% methane versus 35% CO2. So it actually is starting to lose its flammability, let's say, the ability for this methane to burn in the waste gas burner, or also in the boiler. Remember, we got to boil water, or keep water hot rather, to kind of keep the temperature constant. So the biogas mixture is starting to weaken. It's not as potent. So stop feeding and stop the sludge withdrawal. Don't take sludge out of the digester, and don't put any more sludge into it. Keep it mixed. Make sure the temperature remains constant. Don't let the temperature fall. If the biogas is not burnable in your boiler or your hot water heaters, then you may have to switch to natural gas to supplement, so that you do have the ability to keep the water warm. Transfer some seed sludge from a healthy secondary digester. So going back to the pictures, we talked about valves that are there that you can transfer from one to the other. So you may be now valving it so that you can pump from the secondary digester into the primary, which the secondary digester hopefully has some good sludge in there, some stable sludge with alkalinity in it, and that will help speed up the recovery of the primary digester. So you're kind of using your own sludge in the secondary digester to seed the primary digester and give it some healthy bacteria and also the alkalinity. So at this point, you're not mixing up bags of lime or using sodium carbonate, soda ash. You're just using your own seed sludge to try to correct it. So at this point, notice that there's nothing mentioned on this slide about the pH. The pH has not really changed much at all at this point. If the pH was 7.2 in the previous examples, it's still right around 7.2. So the pH has not really fallen yet. So let's just look at a worst case scenario. And this is the picture showing you how you can transfer sludge from one to the other. And you may have to transfer back through this pump back into here from the primary or secondary. And what if you get to the 0.8 to 1 or even higher, equal to or greater than 0.8 to 1? So now the biogas becomes unburnable. The methane fired boiler water heater won't stay running. It's got too much carbon dioxide in it. The pH will now start to drop. We'll actually start to get the pH dropping from, say, 7.2. Now we're down into the 6.8, 6.7 range. It's getting closer to 6.5 than you want it to. The pH is now dropping. That's why it's not a good process tool to use, because now the boiler or the digesters are already upset by the time the pH falls. So watch out for that. Stop feeding, obviously. Don't put any sludge into it. Keep it mixed. Keep the temperature constant. And guess what? Now you're going to be feeding some external alkalinity. This is where you're going to mix up bags of lime or some kind of chemical to feed into there slowly. Do not overfeed it, because it's a very volatile reaction when you put a high pH chemical into a low pH environment, and you're going to have some issues. So you got to feed it very cautiously. The chemicals of choice are sodium bicarbonate, soda ash. Notice that we don't have sodium hydroxide on here. Sodium hydroxide is known as caustic soda. It doesn't really have the same, let's say, efficacy or bang for the buck as far as getting alkalinity in there as sodium bicarbonate or soda ash does, because it's the carbonates that really give it the alkalinity that you're looking for. Sodium hydroxide can raise the pH up, but not really give you the alkalinity boost that you're looking for. So that's why we don't even show sodium hydroxide or caustic soda on here. So keep it mixed, add a source of alkalinity. You're probably going to get, some bags of lime and mix them into a slurry, and then feed that slowly. So when the volatile acid ratio finally gets too high, the pH will now fall. So the process control of a digester is not to use the pH as the process control tool, but use the volatile acid alkalinity ratio. So that's what we're saying on this one. The digester can actually be sour or stuck before the operator is even aware of it. Let's take a look at some data. So we've got indicates a digester getting sour. So we see week number 5. Let's just say the information shows week number 5 for some reason, and then we have week number 27 for some reason. But we have a whole bunch of daily data. We have pH, volatile acid, and alkalinity. And I'd like to just point your attention to the red box here, the red highlighted area. So just look at the averages. Try not to get caught up in all of this data. This doesn't really help us. It just sometimes makes it more difficult to see what I want you to see. So notice the pH, 7.2 on week number 5. The pH over here, week number 27, has dropped. The pH has dropped. So we know we're probably in a sour digester situation in this time period. The volatile acid, when the plant was running good, when the digesters were good, was 225 into 2,607 alkalinity. So that's a pretty good ratio right there. That's actually less than the 0.1 to 1. What about over here? Now we have 2170 of alkalinity, but 1724 of volatile acid. So we are way too high on the volatile acid in this situation. So the actual numbers show us something very, very similar to what we would like to see in week number 5. But look what happened in week number 27. It went to 0.8 to 1. And how you work that math out, by the way, is just divide 1724, divide that by the 2170, and I come up with 0.79 when you do the division. So rounded up would be 0.8. So that's how we come up with that number. So that would be a digester getting sour or already sour. All right, when a digester gets sour, several methods can be used. Use seed sludge from another digester. That's usually readily available. It's the top choice. I would say it's your best choice because it's the same temperature, hopefully, and your own bacteria and your alkalinity and all that. So usually that's one of the better choices. Plus, it's already there. It's free. It's not as difficult to handle as it would be like, mixing up bags of lime, which is not fun at all. The lime has to be mixed into a slurry and can be quite messy. Sodium bicarbonate, sodium carbonate, and magnesium hydroxide are shown here. These are good ones to use. But notice we have in red print here, caution must be exercised when you add a caustic chemical to a sour digester. Remember, these are 2 different pH ranges. And one of the things that could happen is lime, especially with the calcium hydroxide components, can combine with carbon dioxide and essentially converting that into other forms, which then with the collapse of that gas, the carbon dioxide gas, can actually form a dangerous vacuum inside the digester. So you don't want to be drawing in oxygen because you have a vacuum forming inside this digester. You don't want to be drawing atmospheric air in from the pressure relief valves, pressure and vacuum relief valves. And you certainly don't want to cause any damage to anything. So you got to be very cautious, add the lime in very slowly. It's a very high pH chemical. That's why a lot of people tend to divert to, say, soda ash. It's a little bit less volatile reaction. So what happens when your digester gets sour? Well, in the part 1 video, I showed you the pictures of Homer Simpson, and I said how great it is that our bodies are just like anaerobic digesters, or vice versa, right? So if you forget how to handle an anaerobic digester, or what causes it to get upset, or how to fix it, just think about your own human body, because it's so similar. So you might reach for maybe Pepto-Bismol or Tums. You're actually adding alkalinity sources to your gut to neutralize some of these acids, or coat, or somehow relieve that pain. Alka-Seltzer is basically calcium carbonate or sodium carbonate tablets mixed, dehydrated and put into, you put that in water and it fizzes up and it makes this alkalinity that you drink. In some cases, personally, I just put a teaspoon of this baking soda into a glass of water, 12 ounces of water with a teaspoon of baking soda, and mix that. And I use that at home because it's essentially the same thing. So it tastes a little salty, obviously the sodium, and be careful because you do end up usually getting some, a little bit of gas buildup reaction in your gut. You end up burping a little bit, obviously, but that's how these things work. Got to watch out. So we got bags of alkalinity at one of the anaerobic digester facilities I worked at. You can kind of see that some of the bags are open. A lot of the water distribution or collection system guys will grab this and use it for sewer spills and stuff like that. But we keep them on hand at digester facilities all the time because you just never know when you're going to need it for your anaerobic digester. So here's our digested sludge going onto a drying bed from an old anaerobic digester, got some grease in there. If you have any questions on this material or content, or you're not sure of something, you want to, comment or write me, I would gladly appreciate that. Check us out on Facebook again, keep up with us on our website, and I hope that this was helpful. So part 1 goes along with this. This was part 2. Hopefully that both of these helped you guys out. So I enjoyed helping you out with these. And again, good luck on your exams and have a great day. Thank you. Bye.